Okay, let's look at some structural issues in this video. First, we're going to concern ourselves with constitutional isomers. Sorry, I didn't set up the pin yet here. All right, so isomers, this is a term here we encounter very frequently in organic chemistry. These are chemically different compounds with the same molecular formula. The easiest and most obvious type of isomer we have is called a constitutional isomer. Constitutional isomers differ in atom connectivity. There are other types of isomers which are more subtle. We'll cover those, though, as we get to them. Let's look at the most obvious ones first. Okay? All right. And another fundamental thing about isomers is as the molecule gets larger, the more possibilities we have for creating isomers. Okay? So let's start with something simple. C2H6O. For this molecular formula, there are two isomeric compounds. One is called dimethyl ether, shown here, which just has an oxygen with two CH3 groups on it. And the other constitutional isomer of this formula is ethanol. Okay, we could probably appreciate, knowing that ethanol is the major ingredient in intoxicating beverages, that these two compounds, even though they have the same formula, do not have the same properties. Dimethyl ether is a very toxic compound. You could not just throw dimethyl ether into a bottle of tequila and have it imitate the same effect that ethanol has. Okay? All right, so these are structurally very different compounds. So formula alone cannot describe an organic structure. That's, I guess, the take-home lesson from this discussion. Okay? As we go to C3H8O, there are three isomeric compounds. We can have isopropyl alcohol, rubbing alcohol here, N-propyl alcohol, not totally sure what that's used for, and ethyl methyl ether. I don't think that compound's really used for anything. Okay? All right. But you see that these simple compounds illustrate the general trend that formula alone cannot describe the structure, and that as we get more and more atoms in our formula, we create more and more isomer possibilities. Okay, let's look at something that may be related to constitutional isomers, but really isn't, and this is called resonance. Resonance comes about when we have a confusion of the electron density when we're asked to draw the Lewis structure. Okay, so let's say somebody tells us to draw the Lewis structure or Kekulé structure for N2O nitrous oxide, knowing only that nitrogen is the central atom. All right, there are two possible answers that people might want to give here for this question. One is compound A, where we have a nitrogen-nitrogen triple bond and a nitrogen-oxygen single bond. Okay. Another possibility that people might come up with is structure B over to the right here. And here we have a nitrogen-nitrogen double bond and a nitrogen-oxygen double bond. Okay? We can't draw this compound without having a formal charge somewhere. In the A structure, we have a nitrogen with a positive charge and an oxygen with a negative charge. And in the B structure, we have one of the nitrogens has a negative charge and one of the nitrogens has a positive charge. Okay. All right. This is a situation called resonance. Okay. A and B are resonance structures. They're not constitutional isomers because the connectivity is the same. Constitutional isomers require that the connectivity is different, okay? In both of them, we have a nitrogen central atom bonded to another nitrogen and an oxygen. Okay? Resonance structures differ in the placement of electrons, but not in the placement of atoms. Okay? All the connectivity has to be the same. The only difference is how we are distributing the electron. Okay? The true structure is a blend of these two structures. If you actually were able to take a picture of the molecule with a camera, you would find that it looks like this intermediate structure here called the resonance hybrid. The resonance hybrid is just going to take the structures that are common to each feature. Okay? All right, so in both of these, the nitrogen-nitrogen bond is at least a double bond. Okay, it has the left side nitrogen has a lone pair in both structures. There's at least a single bond between nitrogen and oxygen. The difference here is the degree of bonding. We're going to give it this pseudo half bond here to signify that there's some sort of bonding interaction present. Okay? All right. When two things are resonance structures, we use this arrow right here. This is double-headed arrow, and this is called the resonance arrow. Okay? And this tells us that we have resonance going on. Okay? In this case, we can see that resonance form A and resonance form B are technically different, and if the only directions in the problem were draw N2O where N is the central atom, I have to give full credit to both A and B as the answers. But there actually is something better about A than B, and that's the fact that in A we have the negative charge on oxygen, which is more electronegative. Compared to B, which has the negative charge on nitrogen, which is less electronegative. Okay, so A is probably the more important resonance form. The resonance hybrid that you construct would have to look more like A than it does like B. All right, the way this is the first introduction we're going to have here to something called aeroformalism. This is a very important thing in organic chemistry. It allows you to bookkeep where the electrons are very accurately. And if you just bite the bullet and rigidly use arrows the right way, you're going to find organic chemistry to be a very easy class. Okay? All right, so we can signify the turning of A into B through this set of arrows here. Okay, so the arrow on the right shows the lone pair of electrons moving between nitrogen and oxygen, basically creating the second bond of the multiple bond. And it shows the arrows or the electrons in one of the three bonds of the nitrogen-nitrogen triple bond going out to create the lone pair. Okay, so this is basically what's happening here. That lone pair became the second bond of a multiple bond, and the third bond of this multiple bond here became another lone pair right here. All right, so these arrows are signifying the way the electrons are reorganizing in this structure. Okay, so this is called aeroformalism. Arrows must start from an electron pair. This is usually a lone pair or a bond, and that both of these arrows are required. If we had only the right arrow, we would create a situation where nitrogen had 5 bonds to it. Okay, if we only had the right arrow, we would have nitrogen with not enough electrons. Okay, so use of one arrow would give the middle nitrogen too few or too many electrons. All right, so this is the way we are going to represent organic reactions and resonance structures both in this class throughout the next 24 plus chapters. All right. Let's look at another type of resonance, some more resonance forms here. Here's a simpler molecule, ozone. If you're asked to write the resonance structure for ozone, these are the structures you would write. So even though technically these two structures right here, this one and this one, really look the same. It looks like someone just took the left structure and did a horizontal flip on it. Okay, and that's basically what happened. But these are resonance forms, okay? There's some, if you look at all the bonding character in these two, we would construct a resonance hybrid that looks like this, that would be completely symmetrical. All right, and these are called degenerate resonance forms. These are, even though they're equal, they're still both contributing to the structure. All right, so let's look at the consequences of resonance in this structure. No one oxygen atom here is holding a full negative charge. In the resonance hybrid, one of the oxygens has a half a negative and the other oxygen has half a negative, but the central oxygen has a full positive because it's positive in both forms there. Okay, let's look at the acetate anion, and we'll see some chemical consequences here. All right, so we can write a resonance form where we transform the oxygen, one of the oxygen lone pairs into a double bond, and then take the second bond of the double bond and transform it into a lone pair. Again, these look like just in this case, a vertical flip operation, but when you think about the resonance hybrid, it's has actually some very important reactivity consequences. In the anion here, acetate anion, the negative charge is shared by two atoms, and we call this process special term, delocalization. Okay, we don't have the negative charge all at one place. All right, so this accounts for why acetic acid is a stronger acid versus, we'll say, ethanol. When we pull off the proton, the negative charge is shared between two oxygens in acetic acid. When we pull off the proton in ethanol, the negative charge has to exist at the only oxygen that we have. Okay, and the last one we're going to look at is aniline. And this is going to become important in December. It's one of the very last things we talk about in chapter 12. Okay, but here you can see how we can delocalize the negative charge. We have a special nomenclature for these positions, ortho, meta, and okay, I can't go over there without causing some things to happen with the slideshow presentation, but the position opposite we'll call the para position. All right, so what you see here is that when we involve the double bond in resonance interaction with the nitrogen lone pair, like you see with this set of arrows here, we start to put negative charge at the ortho and para positions of this molecule. And this is a very important aspect of the chemistry of this molecule. We're going to see in chapter 12 that positively charged things are attracted to the ortho and para positions of aniline. Okay, all right, so let's look at some of the rules for resonance. Okay, two resonance forms have to have the same connectivity. All right, so we're going to say that this resonance form here, this resonance form interaction that we're showing on the left here is perfectly acceptable. Okay, here's the arrows that we're writing. Okay. And there's no change in the connectivity. But in this one over here, there is a change, okay? The bond line diagram, remember there's a hydrogen here. But if we look at this carbon here, it has one hydrogen. And this same carbon here now has two hydrogens. This group out here has three hydrogens. And then here, it now only has two hydrogens. So therefore, these are not resonance forms because the connectivity has changed. Okay, no first row, that means boron to fluorine atom can have more than 8 electrons. Okay, so we're going to say that these two are resonance forms here. Okay, you can have fewer than 8, but you can't have more than 8. Okay, so if we look at the electron count around carbon and oxygen, this is what you see there, and all that's really happening is that lone pair is becoming a bond. Okay, so the one on the situation on the left is okay, but on the right, we can't consider this resonance form here to be a serious resonance form. It violates the octet rule. There are 10 electrons at carbon. Carbon has 5 bonds to it. Okay, each resonance form has to have the same net charge and the same total number of electrons. Therefore, these two compounds down here at the bottom would not be resonance forms because their electron count is different. Okay, if we count electrons in lone pairs and double bonds, it's 2, 4, 6, 8, 10, 12. 12 valence electrons there. Here's 2, 4, 6, 8, 10. There's only 10 valence electrons there. Therefore, these can't be resonance forms. All right, if you just went ahead and put in the formal charges, you would see very obviously that they're not resonance forms. Okay, the one on the left has a negative charge. The one on the right has a positive charge. All right, so they have to have the same electron count. All right, let's look at the rules for determining which resonance form is better. Okay, the better resonance form is going to have less charge separation. All right, so in the top one, we can see that in the resonance form on the left, every atom is neutral in its natural valence state, whereas in the right, every carbon has a negative charge and oxygen has a positive charge. They still have 8 electrons. They haven't violated the octet or anything, but the resonance form on the left is the one that's going to be better. Now, you cannot ignore the less important resonance form because, as we will see, compounds like this, the minor resonance form can often explain a lot about the reactivity of this compound. For example, positively charged things, I'll just draw generic electrophile E+ right here, is very attracted to that position in this type of compound. Okay, all right. But the one on the left is the one that's more important. That's more representative of the structure, and the resonance hybrid that you generate would look much more like the one on the left than like the one on the right. All right, the better resonance form places the negative charge at the most electronegative atom. We've encountered this one before. All right, so the one on the left has negative oxygen. The one on the right has negative nitrogen. Oxygen's more electronegative, thus we have to consider that to be the more resonance form. And again, we cannot completely ignore the minor resonance form because in many cases we might see reactivity characteristic of the other resonance form. But as far as like what is the one most representative of the structure, it's the one on the left. Okay, the better resonance form will have the maximum number of covalent bonds without violating the octet rule. If we look at this bottom case, we find, we just did this a few minutes ago here, this one has a 6 electrons there and 8 electrons there. If we donate that electron pair to make another covalent bond, we get 8 and 8. Okay, so we can see that there's an additional covalent bond in the resonance form on the right. Thus, that is the more important resonance form, and that's more representative of what this compound would look like. Okay. All right. And again, we cannot ignore the minor resonance form, because I can tell you that we'll just call it generic nucleophile or anion, whatever, is generally attracted to that position right there. So it's still, even though it's the minor resonance form, it does contribute to an overall picture of the reactivity of that compound. All right, we'll end this video here by an exercise. You're just going to tell me yes if they're resonance forms and no if they're not. And if they are, we're going to choose the better one. If they're not, we're going to explain why they're not. Okay, top case. No octet rules are violated. These are resonance forms. There's no change in connectivity. And the one on the right would be better because there's an additional covalent bond. Okay, and the one on the left, it's very obvious that they're not, because for the first, at first glance, you can see that they have different charges, and there's they actually have different formulas. There's an extra hydrogen in the one on the right relative to the one on the left. Okay, so these have different molecular formulas. They cannot be resonance forms. All right, and the next one, oxygen, there's an OH bond. In this one, there is no OH bond. These could not possibly be resonance forms. These are constitutional isomers because they do have the same molecular formula. The hydrogen's attached to a different atom in each one, thus they can't be resonance. All right. Examples 2, 3, and 4 in this problem here are all kind of similar, but in this last one, we're going to realize that they actually are resonance forms. The connectivity is the same. The charge is the same. It's negative. And the better one is the one that has the negative charge at oxygen. That's what the structure of this molecule here is. It's called the enolate. It'll be important in chapter 20. This resonance form here is called the carbanion resonance form. And we're going to find that even though the carbanion resonance form is not the most important resonance form, it actually does give you a good picture of the predicted reactivity of this. I can tell you what's going on here is that the carbon-oxygen double bond is very strong, and these compounds react in such a way as to preserve it. So this is where this video is going to end. We're going to look at the next one's going to be about molecular shape and electron pair repulsion and dipole moments. Okay?